Welcome to my channel. In this video, I will discuss regular point, singular point, and classification of singularity. Mainly, I will focus on classification of isolated kind of singularity, that is pole removable singularity and essential singularity. Let's start with the definition of regular point. Suppose we have a function f from d to c, that is, it is a complex valued function, and d is a subset of c. Is domain of definition of the function f. So z0 is a point in D. This is called a regular point of f if fz is analytic at the point z0. For example, if I take fz equal to e power z. Now e power z is an entire function, so I can say each point of the complex plane is a regular point of the function fz. Similarly for sin z, cos z, these are all entire functions. So every point on the complex plane is a regular point of those functions. Now let us go to the definition of singular point. It says a point z0 is called a singular point or a singularity of the function f if firstly the function is not analytic at the point z0, but every neighborhood of z0 contains at least one point at which the function fz is analytic. The second point is the most important point to check whether a point z0 is a singularity of the function fz. Let's take fz equal to z bar. For this function, we'll determine what are the regular points and the singular points. Now, according to the definition of regular point, a point z0 is a regular point of the function fz if the function fz is analytic at the point z0. Now, fz is analytic at the point z0 if and only if fz satisfies Cauchy-Riemann equations, that is ux equal to vy and uy equal to minus of vx for all xy in the neighborhood of z0, that is denoted by nz0, and uv, ux, ui, vx, vy all are continuous in the neighborhood of z0. So let us check what are the points at which the function fz is analytic. So for this, we can write this as x minus of iy. So here the real part is x and the imaginary part of this function is minus of y. So if we partially differentiate u with respect to x, we get 1 and uy equal to 0, vx equal to 0 and vy equal to minus of 1. So here we can see ux is not equal to vy for all xy in the complex plane. So the first equation of Cauchy-Riemann equations is not satisfied for all xy in the complex plane. So Cauchy-Riemann equation does not hold in the neighborhood of z0. So here we can see the function fz is not analytic at an arbitrary point z0. So here we can see the function fz is nowhere analytic. So the function fz has no regular point. Now about the singularity of the function fz, we observe that the function fz is not analytic at any point z0 in C. But that does not mean all the points in the complex plane are singularities of the function fz, because there does not exist any neighborhood of the point z0 that contains at least one point at which the function fz is analytic. So we can say fz has no singularity. Next, the classification of singularity. So singularity can be classified as isolated and non-isolated kind of singularities. So what is called isolated singularity? A singularity z0 of a function fz is isolated singularity if fz is analytic in some deleted neighborhood of z0. That means about z0, if we can form some neighborhood where except at the point z0 the function is analytic at every point. That means the function fz is analytic in the punctured disk, or we can say except the point z0 in this neighborhood there would be no other singularity of the function fz. Then we can say z0 to be isolated singularity of the function fz. For example, if we take fz equal to 1 by z minus 1 into z minus 2. So here the singularities are z equal to 1 and 2. Now whether they are isolated singularities, so 1 and 2 are the singularities of the function. Now with respect to the point 1, we can form a disk of radius 0.5 where the function is everywhere analytic except the point 1. So we can form a neighborhood in dashed of 1, that is the deleted neighborhood of 1, where the function is everywhere analytic. That is, this neighborhood does not contain any other singularity of the function fz. Similarly, about the point 2, also we can form a neighborhood where the function is everywhere analytic except the point 2. So there is no other singularity of the function fz. So 1 and 2 are isolated singularities of the function fz. Similarly, if we take fz equal to 1 by sine z. So what are the singularities of the function? For this, you can see the zeros of the function sine z are the singularities of the function fz. So for singularities, we'll equate sine z to 0 and we'll get z equal to n pi, n equal to 0 plus minus 1 plus minus 2, etc. There are a lot of singularities of the function z. So we have to determine the nature of this singularity, that is whether it is isolated or non-isolated. So here you can see, so 0 is a singularity. Next, pi, minus of pi are the singularities. 2 pi is a singularity. Minus of 2 pi is also a singularity, and so on. So here about 0 we can form a very small neighborhood where the deleted neighborhood, that means the function fz 1 by sine z is analytic at every point over here except the point 0. So 0 is the only singularity present in this disk. Similarly, for about minus of pi, we can form a disk where a neighborhood, a deleted neighborhood of minus 5 where the function is everywhere analytic. So each of these singularities are, these are all isolated kind of singularities. Next, we'll go into non-isolated singularity. So it is defined as, on the contrary to the isolated one, here you see a singularity z0 of a function fz is said to be a non-isolated singularity if every neighborhood of z0 contains at least one singularity of the function fz different. That means we cannot construct any neighborhood of z0 that is free from some other singularity of the function fz. That means we cannot find any neighborhood of z0 where the function is analytic at every point except the point z0. For example, let us take fz equal to 1 by sine 1 by z. Now the zeros of this part sine 1 by z are the singularities of the function fz. So first determine the singularities of the function fz. 0, that means 1 by z equal to n pi, n belongs to z. So here the singularities are 1 by n pi, n belongs to z. Singularities of fz are zn and their limit point 0. Now, according to the definition of limit point, a point z0 is a limit point of a set case if every neighborhood of z0 contains a point of s other than z0. 0 is a limit point of the set of all singularities of the function fz. So here we can say every neighborhood of z0, that is 0, contains some member of E other than 0. So every neighborhood of the singularity 0 contains a singularity of fz other than 0. So here we can say 0 is a non-isolated singularity. But 1 by n pi for n equal to plus minus 1, plus minus 2, etc., they are all isolated singularities. Because the singularities 1 by pi, minus of 1 by pi, 1 by 2 pi, minus of 1 by 2 pi, and so on. These are the singularities. For each such singularity, we can construct a neighborhood where the function fz is analytic everywhere except the point 1 by pi. So these are all isolated singularities. The 0 is non-isolated singularity, and 1 by n pi for n equal to plus minus 1, plus minus 2, etc. are all isolated singularities. Next, let us take 1 by cos 1 by z. So to determine the singularities of fz, we'll equate cos 1 by z to 0. That is equal to cos 2n plus 1 pi by 2. So the singularities are zn 2 by 2n plus 1 for all n belongs to z, and the limit point of this zn the limit point is 0. So these are the singularities of fz. So like the previous sum, 0, since 0 is limit point of Zn, that is 2 by pi 2n plus 1. So 0 is non-isolated singularity, and all Zn are isolated singularities. Next, let us go into classification of isolated singularity. Isolated singularity can be classified into three categories. One is removable, the second one is pole, and the third one is essential singularity. Now let Z0 be an isolated singularity of the function fz. Now this Z0 is a removable singularity. Z0 is removable if limit z tends to Z0, fz exists finitely in C. Now Z0 is called a pole if Z0 is a pole if limit z tends to Z0, fz equal to infinity, and Z0 is essential kind of isolated singularity if limit z tends to Z0, fz does not exist. For example, if we take fz equal to sine z by z, so here you can see z equal to 0 is an isolated singularity of the function fz. So now we have to check what kind of singularity it is, whether it is removable or pole or essential kind of singularity. So if we take limit z tends to 0 fz, so this is equal to 1, which exists finitely. So 0 is a removable singularity of the function fz. So if we redefine fz as sine z by z whenever z is not equal to 0 and 1 whenever z is equal to 0, then the function fz becomes analytic at the point 1. So here we can conclude an isolated singularity z0 of a function fz is removable singularity of fz if fz can be made analytic at the point z0 by defining fz at z0. Next, let us take fz equal to z square plus a square by z minus of ia for z is not equal to ia. So here we can see z equal to ia is an isolated singularity of the function fz. Now let us check whether it is removable singularity. For this, we'll take limit z tends to ia, z square plus a square divided by z minus of ia, which is equal to limit z tends to ia, z plus ia. So from here we are getting the limit as 2ia. So here we can conclude z equal to ia is a removable singularity of the function fz, since this limit exists finitely. So now we can see, since this is a removable singularity, we can redefine the function fz as z square plus a square by z minus of ia whenever z is not equal to ia and is equal to 2ia whenever z is equal to ia. So with this definition, the function fz becomes analytic at the point ia. Next, to identify whole kind of isolated singularity, let's say 0 be an isolated singularity of a function fz. Now, if limit z tends to z0, fz is equal to infinity, and there exists some natural number m such that limit z tends to z0, z minus z0 power m into fz exists finitely and which is not equal to 0, then we say z0 is a pole of order m. Now, if m is equal to 1, that means if it is a pole of order 1, then z0 is called a simple pole. Here we observe two important points in the definition of pole. Firstly, if z0 is a pole, then as z tends to z0, fz approaches to infinity. So from here we conclude fz is unbounded near z0. So whenever we have a pole at z0, then near z0 the function fz is unbounded. But if z0 is a removable singularity, there we have seen limit z tends to z0, fz is finite. So this means if z0 is a removable singularity, then fz is bounded near z0. The next important point that we can generate from this expression, so z0 is a pole of order m. If and only if we can write fz as phi z by z minus z0 power m, where phi z is analytic in some neighborhood of z0 and phi z0 must be not equal to 0. This is because, so if we write fz in this form, so from this expression we can see limit z tends to z0, z minus z0 power m into fz, that is phi z by z minus z0 power m. So from here we are getting phi of z0, which must be not equal to 0, so that z0 be a pole of order m. Okay, so equivalently, we can identify a pole of order m by using this expression also. That means if we can write a function fz in this form, phi z by z minus z0 power m, where phi z is analytic in some neighborhood of z0 and phi z0 is not equal to 0, then z0 is a pole of order m. Let us solve some examples. Let fz equal to e power z by z square. So what are the singularities of the function fz? So here, if we equate this to 0, we'll get z equal to 0 is an isolated singularity of fz. Now here we can say this can be written as pi z by z minus 0 power 2, where our pi z is e power z, which is analytic in the neighborhood of 0. And the second important point is phi of 0 must be not equal to 0. So it is e power 0 is 1, which is not equal to 0. So all the criteria are true. So here we can conclude z equal to 0 is a pole of order 2. Next, let us take z equal to 1 by z plus 1 whole square z minus 3. So here how to determine the singularities of the function fz. So here one important point is if a function can be written as 1 by fz, then the singularities of 1 by fz are the zeros of the function fz. So just we have to equate this to 0. So to get the singularities, we'll equate z plus 1 whole square, z minus 3 to 0. So the zeros of this function are the singularities of the function fz. So here we are getting z is equal to minus of 1 and 3. So these are the singularities of the function fz. Now we have to determine the nature of the singularities. Firstly, they are isolated singularities. Next, we can see if we write fz as 1 by z minus of 3 divided by z minus of minus 1 whole square. So here our phi 1 z is equal to 1 by z minus of 3, which is analytic in the neighborhood of minus of 1, and phi 1 of minus of 1 is equal to 1 by minus of 1 minus of 3, that is equal to minus of 1 by 4, which is not equal to 0. So here we can see minus of 1 is a pole of order 2. Secondly, if we can write fz as z plus 1 whole square divided by z minus of 3. So here our phi 2z is 1 by z plus 1 whole square, which is analytic in the neighborhood of 3, and phi 2 of 3 is equal to 3 plus 1 whole square, 1 by 16, not equal to 0. So here we can see Z3 is a pole of order 1, that means 3 is a simple pole. Let us try to identify the nature of isolated singularity through Laurent series expansion. In the video regarding Laurent series expansion, we have seen if a function fz is analytic in a deleted neighborhood of z0, that means if z0 is an isolated singularity of a function fz, then we have a unique Laurent series representation of the function fz about z0 as equation number 1. So, Laurent series expansion is an important tool in characterizing the nature of isolated singularity. So, whenever we have an isolated singularity z0 of a function fz, We can write its Laurent series expansion about Z0 in this form 1. So the first part of Laurent series expansion contains the negative powers of Z minus Z0, which is called the principal part, and the second part contains only the positive powers of Z minus Z0. This is called the analytic part. Now, if in the principal part there are only a finite number of terms present, then we say Z0 is a pole kind of singularity. That means if there exists a positive integer m such that a minus of m is not equal to 0, that means the coefficient of z minus z0 power minus of m is not equal to 0, and a minus of n is 0 for all n strictly greater than m. That means after z minus z0 power minus of m, all the terms are zeros. So in this case, we say z0 is a pole of order m. Let us take an example. So let fz equal to e power z by z cube. So here z equal to 0 is an isolated singularity of the function fz. So now if we try to expand this function, we'll get the expansion of e power z is 1 plus z square by 2 factorial plus z cube by 3 factorial plus z power 4 by 4 factorial and so on divided by z cube. Now this can be written as 1 by z cube plus 1 by z square plus 1 by 2 factorial into z plus 1 by 3 factorial plus z by 4 factorial and so on. So here we can see this is the principal part of the Laurent series expansion about the point 0, and this is the analytic part that contains only the positive powers. So here we have only 3 terms present in the principal part, and here a minus of 3, that means the coefficient of z minus 0 power minus of 3 is equal to 1, and after that, that means a minus of 4, a minus of 5, etc. That means a minus of n is equal to 0 for all n strictly greater than 3. So here we can conclude that z equal to 0 is a pole of order 3. Next, let us take fz equal to sine z by z power 5. So here also z equal to 0 is an isolated singularity. So let us try to determine the nature of this isolated singularity. So for this, we'll expand fz. Now the expansion of sine z is z minus z cube by 3 factorial plus z power 5 by 5 factorial, z power 7 by 7 factorial and so on divided by z power 5. So this can be written as 1 by z power 4 minus of 1 by 3 factorial into z square plus 1 by 5 factorial minus of z square by 7 factorial and so on. So here we can see there are only finite number of terms present in the principal part. So this is the principal part that contains only the negative powers of z minus 0, and this is the analytic part that contains the positive powers of z minus 0. In the principal part, we have the coefficient of z minus 0 power minus of 4, that is equal to 1, and after that all the coefficients are zeros. That means a minus of n equal to 0 for all n strictly greater than 4. So our conclusion is z equal to 0 is a pole of order 4. So here we can say whenever z0 is a pole, then in the Laurent series expansion about z0, the principal part contains only finite number of terms. Next, regarding the essential singularity and removable singularity, we have if the principal part of Laurent series expansion of fz about z0 contains infinitely many terms, then z0 is essential singularity. And if the principal part of Laurent series expansion of z about z0 contains no term, that means there is no term present in the principal part of Laurent series expansion, then z0 is a removable kind of isolated singularity. For example, let us take z equal to sine z by z. We have already considered this function and we have seen z equal to 0 is a removable singularity. Now we try to determine the nature of the isolated singularity z equal to 0 from Laurent series expansion. So if we expand sine z, we'll get z minus z cubed by 3 factorial plus z power 5 by 5 factorial and so on divided by z. So from here we are getting 1 minus of z square by 3 factorial plus z power 4 by 5 factorial and so on. So here we can see the principal part contains no term. So only the positive powers are present over here. No negative power is present. So z equal to 0 is a removable singularity. And we can redefine the function fz as sine z by z whenever z is not equal to 0. And here the constant term is 1. So we'll assign the value 1 at the point z equal to 0 so that the function fz becomes analytic at the point 0. Our next example is fz equal to 1 minus cos z divided by z square. So here, if we equate this to 0, we'll get the singularity. So z equal to 0 is an isolated singularity. Now let us try to expand this function. The expansion of cos z is 1 minus of z square by 2 factorial plus z power 4 by 4 factorial and so on. From here we are getting z square by 2 factorial minus of z power 4 by 4 factorial divided by z square. And it is 1 by 2 factorial minus of z square by 4 factorial and so on. So here also we can see there is no term present in the principal part. So z equal to 0 is a removable singularity. And we can redefine the function fz as 1 minus cos z by z square whenever z is not equal to 0, and we'll assign at z equal to 0, the value will be 1 by 2, because here we have 1 by 2 as the constant term. So now if we assign z equal to 0, the value of the function fz at the point 0 is 1 by 2, then the function fz becomes analytic at the point 0. Next, let us take z equal to e power 1 by z. So here z equal to 0 is an isolated singularity. For z equal to 0, now if we expand the function, we'll get 1 plus 1 by z plus 1 by 2 factorial into z square plus 1 by 3 factorial into z cube and so on. So here we can see there is only negative powers are present over here, and there are infinitely many terms present. So the principal part contains infinitely many terms. So we can conclude z equal to 0 is an essential singularity. Next, let us take z equal to sine 1 by z. So here also z equal to 0 is an isolated singularity. Now if we expand the function, we'll get 1 by z minus of 3 factorial z cube plus 1 by 5 factorial z power 5 and so on. So here also we are getting infinitely many terms present in the principal part. So z equal to 0 is an essential singularity.